everyone and welcome back to SP Learning Labs, where we break down advanced Python topics into clear and professional skills. Today we are diving into 3 essential pillars of writing efficient production grade Python: memory management and garbage collection, type hinting and annotations, iterators and generators. These concepts power real-world systems, improve performance, and help you write cleaner, predictable, scalable code. Let's begin by understanding what's happening behind the scenes with Python's memory management and garbage collection. How Python manages memory automatically. Unlike low-level languages like C or C++, Python does have the heavy lifting for you. Imagine a library with a meticulous librarian. Every time you borrow a book, the librarian writes it down. When all copies are written, the librarian clears the shelf. Python works the same way. It tracks the object usage and frees memories automatically when objects are no longer needed. Here is a key idea. Python equals to automatic memory manager plus reference tracker, reference counting and garbage collector. Python's primary mechanism is reference counting. Each object knows how many references point to it. When the count becomes 0, the object is destroyed and memory is freed. But reference counting has a weakness: circular references. Imagine 2 books referencing each other. The librarian gets confused. To fix that, Python uses a cyclic garbage collector through the GC module. It uses generational garbage collection. New objects are checked more often. Old objects are assumed stable and checked less often. This hybrid system prevents memory leaks in large applications. First, let's start with the foundation. Functions as first-class citizens. They can be assigned, passed, and written. That we'll see with an example now. I'm creating a file greetfunction.py. Here I'm writing a function def greet of name, and I'm returning hello and name. Here greet is just an object. After this, we are going to point to the function. This flexibility makes decorators possible. I am writing a say hello equals to greet, and I am writing a print statement, print say hello Alice. Now we are going to save this program and run it. Here we have hello Alice as output. Weak references and slots. Some objects shouldn't increase reference counts, especially cache entries. For that, Python has weak references via the weakref module. Weak references let you reference an object without affecting its lifetime. Perfect for caching, object pools, and observers. Another optimization feature is slots. By default, every Python object stores attributes in a flexible dictionary. Convenient but memory heavy. Using slots fixes allowed attributes and saves memories greatly. This is widely used for performance critical classes. We can inspect and manage the garbage collector using built-in tools. Some common pitfalls. Holding references you don't need. Misunderstanding del, it deletes the name, not the object. Creating complex circular references. Few hidden facts. Python uses hybrid memory management. Slots prevents dynamic attributes. Weak references avoid cache memory leaks. Type hinting and annotations. Type hints don't affect runtime, but they greatly improve clarity, maintainability, and tooling support. They make your intent clear and help teammates and tools understand your code instantly. Static analysis with mypy. To actually check type correctness, we use mypy, a static type checker. If a function expects integers but receives a string, mypy catches it before runtime, preventing hard to debug errors. This is invaluable in large-scale systems. Advanced type system. Python's typing module gives us powerful features. Protocols allow structural typing. If an object behaves like a type, it's accepted, even without the inheritance. Common mistakes and hidden facts. Common mistakes. Overusing any eliminates type safely. Forgetting to update hints after refactoring. Assuming Python enforces types at runtime. Few hidden facts. Type hints are ignored at runtime. Python 3.11 introduced this self-type. Typing extensions backports future typing features. Iterators and generators. Iterator protocol. An iterator is any object that implements the iterator protocol. When no items remain, Python rises stop iteration, which gracefully ends loop. For example, think of an iterator as a bookmark that moves forward one step at a time. Generators and yield. Generators create iterators easily using the yield keyword. They don't store all values. They generate them one at a time. This makes them perfect for large data sets, streaming tasks, and pipelines. Generator pipelines. You can chain generators to create efficient processing pipelines. Python handles one item at a time. No memory waste, no buffering. Advanced generator tools and errors. Generators support advanced features like delegation, sending values, and control shutdown. Delegation simplifies nested logics and keeps generators clean. Now, we'll go into another topic, the closures, the engine behind the decorators. A closure is when an inner function remembers values from its enclosing scope. That we'll see with an example now. Here I am writing a function def outer of message and another function inside it, inner function. And I am writing a print statement, print message. I'm returning the function inner. Hello equals to outer and outer of hi there. Decorators rely heavily on closures. Inner remembers message even after outer finishes. I'm calling the function hello. Let's save it and run it, and we have hi there as an output there. Now coming to function decorators. We'll start with basics. Let's build our first decorator. I'm creating a file here named wrapper.py. The wrapper wraps extra behavior around it. I'm writing a function def of decorator of function. And I'm writing another function def of wrapper. I'm writing a print statement here as print before function runs. Here the decorators are the same. I'm calling the function and I'm stating an other print statement as after the function runs. And I'm returning wrapper. Here we're calling the decorator, writing another function down here, def of say hello. A print statement as hello world. Now we'll call the function say hello. Save this program and we'll run it. Here we can see as function runs and hello world. After the function runs, it is shown as hello world. Now we'll see an analogy here. Think of wrapping a gift. The gift stays the same, but the wrapper adds the experience. That's what exactly this does. Function decorators. Now we'll see decorator with arguments. When decorator needs input, we add another layer. That we'll see with an example now. I'm having a file repeat decorator.py and I'm creating a function def of repeat n. I'm writing another function def decorator of function. And other one def of wrapper. I've told you before the wrapper conditions. Repeat 3 returns a decorator. The decorator wraps the function. Here I'm writing a for loop for in range of n. I'm calling the function and returning the wrapper. And I'm also returning the decorator. Here we'll see the argument @repeat 3. Repeat 3 returns a decorator. That decorator wraps the function. Now the behavior is repeated 3 times. Here I'm calling the function def of greet and printing hi. I'm calling the function greet. Now save this program and we'll run it. Here the hi has repeated 3 times and it has been printed. Multiple and chain decorators. Multiple decorators stack like layers. We'll see that. Here I'm taking styledecorator.example.py as a file and I'm taking def of bolt of function. I'm taking a wrapper function, def of wrapper and returning B and functool and the closing. Here I am writing the bold font plus function and I am closing it. Now I am returning the wrapper. Another function, def of italic. The wrapper function, and inside it I am going to return the italic font. Return italic plus function plus closing tag. @italic applies first. Then the bold wraps over it. As we discussed, this is going to apply from bottom to top. Now I am calling bold function, the italic one, and greet function. Here I am returning hello. Now I'll be printing greet and we'll see the bottom to top execution now. Save this program and we'll run it. Yeah, we have the output hello. Bold, italic, hello and the closing ones. Now, the stacking of filters on a photo as an analogy. That is exactly how this works. First, the brightness, then the contrast, then the color applies. This is how this all works. Now, we'll see another one. Class decorators and functool wraps. Decorators can also be implemented as classes. That we'll see with an example now. Class-based-decorator.py as a file, and I'm writing a class decorator. In that class, I'm writing init function of init self.func. Here, the function becomes an object. Self.func equals to func. Here I am taking another function, call function and a self. I am writing a print statement, class-based decorator. Calling the object triggers call. Here we'll be calling a decorator. These are greater for complex decorators. I'm calling another function def of hello, print hello Python. I'm calling the function hello. Now we'll save this program and we'll run it. Here we can see class-based decorator and hello Python. Now we'll see a small functool wraps. Why functool wraps matters? That we'll see now. I'm taking from functools import wraps. And we can see def of decorator of function. Wraps function. Without wraps, wrapper function loses. Name, doc, module, everything will be lost. Now I am writing wrapper definition. I am returning the function and returning the wrapper. The wrapper is written. Here, wraps is like tagging the original author after remixing the song. That's how it works. Without the wraps, I told you, names, doc, module, all are lost. And that's with wrapper function. Now we'll see few built-in decorators. How this built-in decorators works. Python packs many built-in decorators. For example, from functools we have import LRU cache. LRU cache is imported and I'm writing a Fibonacci function, def of fib of n. If n is less than 2, we'll be returning n. Now return fib of n minus 1 plus fib of n minus 2. Cache stores previous results, so drastically reduces the recursion time. Now I'll be printing Fibonacci of 10. Print then we'll see 5 as input. Here we are getting 5. LRU cache is like remembering all answers to avoid recalculating. So we'll be printing print Fibonacci of 10. Yeah, we can see 55. That's how cache memory is done. That's with the decorators. Now you are going to see the recap and interview questions that are there. Common mistakes to avoid. Forgetting proper termination in custom iterations. Trying to reuse an exhausted generator. Mixing return and yield incorrectly. Fun fact. Generators remember their internal state between calls. Let's quickly recap what we learned today. Memory management. Python uses reference counting and garbage collection to manage memory safely. Type hinting. Improves readability, catches issues early through static analysis, and helps scale large code bases. Iterators and generators. Enable lazy evaluation, ideal for large data sets, pipelines, and efficient loops. Mastering these 3 topics takes your Python from working code to efficient, scalable, and professional code. Great job today. You're building solid foundations. And that wraps up this session. Today, you gain the building blocks behind the Python's efficiency. Memory management, precise type hinting, and powerful iterator patterns. These aren't just features. They are the foundations used in real frameworks, data pipelines, and production systems. If this session helped you grow, make sure to like, share, and subscribe to SP Learning Labs. And let me know in the comments which concept clicked you for today. In the next session, we move into exception handling and debugging tools to help you write safer, more reliable programs. Until then, keep learning, keep building, and keep growing with SP Learning Labs.